Thank you for the invitation. So today's presentation will be about how to develop a product and all the steps along the way. And I will present you my experience how to use LabVIEW in all those steps of development of the next generation detector. Maybe I will start with introducing myself. I started working in 2005 at the University of Science and Technology in Krakow, Poland. In roughly the same time, we started to develop or collaborate with industry, with Rigaku Corporation from Japan. We developed several products together, which I will show today. 2 years ago, I came to US, to New York, to work at Brookhaven National Lab. I'm a research scientist in there. My research goes around hybrid pixel detectors. Those are generally the same devices as you have in the phone, just different photon energies. The X-ray energy is much higher, so the sensor is thicker, pixel is bigger. Our pixels have a lot of functionality, not only simple capacitor, but also amplifier, shaper, digital blocks. We connect those pixels into external sensor, which is just a silicon plate. And then this is the hybrid structure we put on the PCB, connect with wires to have electrical exchange of power and data. When the X-ray photon hits the sensor, we want to collect this cloud of charge. The cloud of charge, roughly having 2,000 electrons, is our input signal, the current pulse. We have to measure. There's no device you can just buy it. You have to implement it, build it. And then we read the data into the PC. We developed several different solutions, basically integrated circuits, starting from one-dimensional through two-dimensional, which is the basically image sensor. The small ones, or high technology nodes, like CMOS 90 nanometer, 40 nanometer, even further, usually serves as prototypes, while the big ones are utilized in commercial devices. All our channels, like pixels, have certain parameters like gain, offset, noise, high count rate capabilities, and so on. They are characterized by certain equations that we have to compare to. So you see, it's a lot of data processing going on, not just an image after all. And then we have to verify if our solution match our assumptions. What are the research then if you want to produce an ASIC? One example can be the charge sharing phenomenon. It occurs when a single photon hits the area in between two channels, then the charge cloud is shared between two channels. And we don't know what was the total amount of charge generated. How to resolve this problem? That was easy for us. Let's sum all the data together and then put comparators between certain channel and all the neighbors. Sounds easy, but the pixel size usually is less than 100 micron. So the solution is really squeezed inside. Then we have an idea how to verify if it works fine. Of course, in simulations. Then we have to develop those simulations. And we can use LabVIEW for that. Our solution was named C8P1. We generated the model of the channel. We generated the signal that goes in, and there was many parameters. The whole idea that I'm presenting just at this slide is the subject of another 1.5 hour presentation, so I'll be very, very short about it, let's say. So LabVIEW allows us to prepare this kind of Monte Carlo simulations and plot the data. That what it shows us that we have a room in the center part where we can work without having additional noise or extra pulses. Basically, it means we can work with the solution when the design is done. And it was very slow, the same slow as any other language, like Python, MATLAB, and any other. because of the number of parameters and number of simulations we had to do. So we could actually accelerate this. We put those Monte Carlo simulations of those two-dimensional matrix into FPGA. We developed certain architecture, which I will not go to too deeply. I will just introduce the certain point of a single channel, how we simulate. This is the simulation of the single channel. Roughly, if you just calculate by hand, it has something like 40 to 60 basic operations. When you use a CPU, you have to calculate one after another. Then the array is 8 by 8, so 64. If you multiply that, it's already a couple of thousands of operations. And then we have to add the noise generation. And the noise generation, if someone uses it, it's quite time-consuming on the Windows machines. In FPGA, we can do everything in one clock cycle, all the computations that I just showed. The cost of it is the noise is not exactly Gaussian, but that's fine, it's close enough. And then we could actually accelerate the computations 4,000 times, generating two-dimensional graphs that were interesting for us within seconds instead of days. We could generate the channel then, not generate, architect. It was designed by ASIC designers. ASIC was fabricated, and we can see it worked fine. It wasn't working too well. It was very slow, so we had to accelerate the processing speed. We went through different solutions. It is just an example of what we do in research. There's so much more. The recent one, which we will present fall this year at Nuclear Science Symposium, is the one where we put artificial neural network inside each pixel of an integrated circuit. So we have hundreds of ANNs calculating our signal. But I will not focus on that at this moment. When the research is done and we design and fabricate our ASIC, then we have to test it. That's where it becomes interesting, because we all know what it means to test electronics. Most of our solutions, all of our solutions actually, exchange the data in a digital way. And surprise, surprise, LabVIEW has a dedicated data for that, digital data type and the digital data graph, where you connect graph directly to the function that performs the acquisition from waveform generator analyzer. You can see your protocol right there. You can just inspect visually if everything works fine or something's wrong. And then, from this bit stream, which is extremely scrambled at some point, we need to extract the analog values. And LabVIEW has options for that. It gives us all the necessary functions to work on digital bit stream, binary waveforms, transfer to numeric waveforms, and eventually show it on the user interface. This is quite long equation, having multiple parameters. Fitting the measured curve to the certain equation is very time-consuming. And having hundreds of thousands of channels becomes ours. Then we have also an option to parallelize all our computation using multiple processors. It's as easy as just using properties of the for loop. It improved 8 times, now it's 16 times with more cores. It allows us to do proper user interface to quickly judge if circuit is working, and then we can put this into system like imaging. Those images are very small. This is just to test the ASIC. Not every test can be done just using Windows machines. Many of those tests requires embedded systems development. Our first step with embedded system development started with the first SBRIO that came out. This is our solution, one of our ASIC connected to the RIO device. The first software we wrote for FPGA was 2012. It was still quite decent. We couldn't use many sub-VIs as it compiled poorly. It was working the whole functionality you just saw was working with 40 megahertz clock. It was enough to verify the ASIC, but was not enough to put it on real experiment. So we had to translate it. I will show later. Then we moved to system on module, which is another SBRIO. If you ask me, it's the best one for various reasons, and I really hope the end of life will be further extended. We could very easily decouple the functionality related to our ASICs and detectors with functionality related to embedded system. We developed two boards. The bottom one here on the picture is related to FPGA, which is single board TRIO. The data stream is realized on the camera link interface. The bottom PCB contains our detector, which you can see on the screen. And then the software stack. This is where the true power of LabVIEW comes, because the whole software stack is in one project window. We can communicate with ASIC using FPGA code. We can supervise the FPGA code with real-time operating system. Then on the Windows machine, we have a frame grabber with FPGA that also has the same, not the same of course, but code written in LabVIEW. Whenever we have an issue, we target right to the point. We don't have to call anybody. We just open the problem and just solve it. And then the nice part is when we can kind of collect some images. We've proven this device to work properly. It was later commercialized. When I moved to Brookhaven 3 years ago, I continue using SBRIO. The latest version is really spectacular. The CPU is very powerful. And maybe I'll not talk too much as the presentation is still long. We use passive cooling with enclosure with very thick layers because we want to completely clean our system from the noise from those PCBs. There are many DC-DC converters, and I just remind you that we measure single electrons of noise. That's very important. So the device looks like on the screen. There's a box inside this, the Rio device. This small dings in here is the wireless USB stick that makes our device wirelessly accessible. And our system, as you can see, is very simple, very simple. It has just an ASIC and some supporting elements. That's why I think SBRIO is very good for prototyping. It streamed out our development. You can see 3 different detectors, different solutions presented at Nuclear Science Symposium last year at the exhibition stage. They all work as embedded devices. I will not talk much about them, as every one of them can be separate presentation. Maybe I will just focus on, say 2 words on this one. Our latest solution of pixelated detector is the first in the world that works truly asynchronously and event-driven. When a pixel obtains an event, which is detect electrons, then it latches certain analog value and passes it out truly asynchronously, not having any clock in the whole system whatsoever. And also acknowledgement of this data is done asynchronously. So there's no noise in the system during data acquisition. What you can see on the screen, yellow is the value taken from analog to digital converter, and the red one is the address of an event. It's all streamlined in FPGA. I know you're interested in just a glimpse of code, so maybe I will show you one example. This is a piece of FPGA code. It has 32 channels, so it goes like up and up and up. And we connected 2 analog devices, ADCs, 14 bits, up to 65 megahertz. I will just read this just for a second so you can read the numbers. Our FPGA code can change this frequency fluently during the operation up to 65 megahertz. It means the SBRIO IO pins are sampled at 910 megahertz per channel. That gives 30 gigabits per second data stream that we use in single board TO. And I'm not counting those 4 clocks that we need to use. It then goes to whole digital signal processing stream, essentially utilizing almost 98% of the FPGA code and almost 90% of lookup tables. Even quicker system is another detector that uses the acquisition of 32 channels, but each channel is sampled at 2.56 gigahertz. This is the sampling rate of I/O nodes, digital I/O nodes on FPGA. It results in more than 56 gigabits per second continuous data stream to be processed by FPGA. Okay, so when we test our solutions, we are ready to introduce it to the industry. But usually when we have it on the table and we verify it works, it doesn't mean it actually works. We think it works. Then we need to use it and verify in real experiment. One of the experiments we use those detectors at is synchrotron. Synchrotron essentially is the brightest X-ray source you can get. One of them is close to here, Argonne. I was collaborating with Argonne for 6 years on those detectors. Another one is in Brookhaven, of course. There's one in Japan, very big one, and a few in Europe. Our first experiment was to get our first device that couldn't get into memory of this small FPGA of the single board TO and translate it to the FlexRIO. It took us the whole 15 minutes to translate. We just redefined IOs and it worked fine. The memory was just a number for us. So we could evaluate if there's any leak of events between frames, and we could actually map the synchrotron current per bunch, which those small bunches of electrons are distinguished by only 153 nanoseconds. It was the first result like that on a hybrid pixelated detector. It encouraged us to go even further with experiments, and we tried the X-ray correlation spectroscopy, which essentially is collecting the large number of frames, at least 200,000 frames, that tells us about the memory that we need to have, with a very high speed, which is 50,000 frames per second. If you calculate, it's a really large stream. And we don't care about images itself. We just care about the correlation between them to verify the internal structure and dynamic behavior of what we are measuring, what we could measure, like a barrier that is on within a brain tissue. How well can a certain drug pass this barrier to keep certain consistency of the brain tissue? Our system that we used at the first place used PXI system and the FlexRIO device with the digital interface. Later on, we changed it for the smaller form factor, which was the FlexRIO that has a Kintex on board and a real-time operating system. Again, the application is very interesting, one of the biggest I've written. It has also an event detection, but I will not go deep into this point. I will just maybe summarize that we got the best results published in physical review letters, where we cover 8 time decades, which was itself the first result of its kind. But also we went into deep microsecond regime with the blue line here that actually could get us information about dynamics of the system. This is how it looked at the beamline. The X-ray beam is going through this tube here, and our solution is this small board that you see on the slide. And then we we get the data within this FlexTrio controller. The picture was taken 2 years after the system was developed, because on the middle, this is the commercial version of this small chip. It's 16 times bigger and works in the very same operation as we defined before using LabVIEW. I will skip the second description because it's very similar, uses similar hardware, and the time is passing quickly, so I have to hurry. When we verify that our solution works well, not only on the table, but also in an experiment, then it becomes interesting, because then we can actually participate in the development of the commercial instrument. Almost every solution we developed in the past ends up in a commercial device, starting with 2008 and one-dimensional detector, going through the two-dimensional detector, which actually was brought to the whole family of detectors. And if you think NI devices are expensive, try to buy one of these. This is the fastest detector in the world you can buy. At the moment, it gets 56,000 frames per second, and you can build as big as you want. The whole wall can work with the speed, with the cost, of course. In the process of development of this detector, we still use LabVIEW. We use it to verify wafers. We use it to trim the device before sending to clients. And if you get the device, if you connect it to the PC, the data you get to the PC is actually taken by the software written in LabVIEW. This is a data server. Just about this application was the subject of my presentation at CLA Summit in Paris 2012. And the application still works, is still under development. It started slowly. At the beginning, it used the frame grabber card. Now it's multiple of frame grabber cards. What the software does, it provides the interface between the camera and the user. Not only it has a standalone application, but also provides a user API for everybody to write their own software. Software was tested for 2 ways: procedural without object-oriented design, using just a multi-thread application, kind of cute message handler. And the other one was object-oriented with actor framework. That version stayed because of long time support. I will not go through this presentation deeply. Maybe I will just summarize that when we get to the final stage, when we develop the commercial detector, only then it becomes interesting, because we can go back to the research and develop the next generation one. And I think I will stop at this point. If you have any questions, I will be happy to answer.
Your last slide had a little comparison between the 2 programming methods. That's actually really interesting, with like pros and cons.
Yeah, it was 10 years ago. In a way, I think there are different views. The researcher, I try to see myself as such, and the developer. So I don't like object-oriented. It slows me down a lot. But for developers and product development, you don't have other choice. Teams change, people change, and you have to keep responsibility. So there's not much choice. Those different views. Basically, this is the summary of what was there. I know I squeezed like 10 large presentations into one. I just wanted you all to know me, what I do. And if you have any questions further, you can ask me. I'd be happy to chat about. Okay. Thank you very much for your attention.